Assalamualaikum warahmatullahi wabarakatuh. Today, I'd like to present our work on heart disease prediction using data mining techniques. So, my name is Nofarha Wanda binti Ruslan, metric number 072586. Before we start our presentation, let me introduce our group members. First, Nofarhana binti Asmawi and Nur Ilya Izati binti Muhammad Nazri. For this project, we select the prevalent heart disease dataset. So, as you can see here, this is the overview of the dataset. In this project, we use a classification technique to predict the presence of heart disease. To perform the classification, we apply three algorithms, yaitu logistic regression, decision tree, and random forest. So let's start with logistic regression. This one is quite simple and fast. It works really well if the data has a straight line relationship, like if increasing age or cholesterol steadily increase the risk of a heart disease. The great part is it's very easy to understand, and that's important in healthcare where decision needs to be transparent. But the limitation is it assumes that straight line relationship, which is not always true with complex medical data. Also, it does not handle things like variable interaction very well, and it can struggle when the dataset is unbalanced. Next, we have the decision tree. This one is more flexible, it can handle more complicated patterns, and it's great because you can actually draw it out. For example, it can give rules like if cholesterol is above this level and age is above that level, then high risk. But the problem is decision trees can overfit. They might work great on training data, but not so well on new unseen data, and even have small change in the data can lead to a completely different tree. Lastly, we use the random forest. This model is like a bunch of decision trees combined. It gives much better accuracy because it averages out a lot of different trees. It also tells us which features are most important, like whether age or blood pressure matters more. The downside is it's a bit of a black box, not as easy to explain, and it takes more time and computing power to run. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Naufaharna binti Asmawi, and I will present part B of this assignment. First, we look at this code. This code were used in this assignment, and I will present more detail about this code on the next slide. There were 5 data preprocessing within the code. First, handling missing values. Missing values were then filled with the mode of each column to preserve categorical integrity without removing rows. Second, data type conversion. Column with string or object types were converted to float to make them usable for machine learning algorithms. Third, target label transformation. The original target feature included multiple values indicating disease severity for binary classification, 0 for no heart disease, 1 for presence of heart disease. Fourth, splitting the dataset. The dataset was split into 80% training and 20% testing, using train test split to evaluate model performance on unseen data. And fifth, feature scaling. Standardization was applied using standard scaler to bring all features to a common scale. This step is crucial for models sensitive to feature magnitude. The feature selection. To improve model performance and reduce complexity, feature selection was performed using select k-best with the ANOVA f-test f-class if. This method ranks features by their statistical significance with respect to the target variable. The top 8 features selected were CP, chest pain type, thal edge, maximum heart rate achieved, slope of ST segment, XN, exercise-induced angina, alt peak, ST depression induced by exercise, CA, number of major vessels, thalassemia type, resting ECG result. Lastly, on part B is the impact on model performance. There were three models that were picked based on their accuracy. The first is logistic regression with 0.9016 accuracy. Second, the decision tree with 0.7541. And lastly, random forest with 0.8525. The logistic regression model achieved the highest test accuracy of 90.16%, indicating that pre-processing and careful feature selection allowed a relatively simple model to outperform more complex ones, like random forest. This high performance also supports the model's suitability for deployment in clinical decision making.
Assalamualaikum. My name is Noor Ilazati Manasri, and my metric number is 072928. So let's begin by talking about how we can build trust in AI system, especially when it comes to sensitive field like healthcare. Trust is the foundation for adoption, and we cannot expect clinician or patient to rely on these tools if they don't understand them or see their value. That's why we have focused on four key principles. First, transparency is essential. In healthcare, where decision can directly impact life, we cannot afford to use black box models. Instead, we use interpretable models like logistic regression where we can clearly see how different inputs, like age or cholesterol level, affect predictions. Tools like correlation matrices or future importance plots help us visually explain how the model reaches its conclusion. This makes it easier for clinicians to trust the system because they can understand how it works. Next is validation and performance. It's one thing to say a model is good, but we need to prove it. That's why we use metrics like accuracy, precision, recall, and confusion matrices. This gives a full picture of how the model is performing. In our case, logistic regression achieved an accuracy of 60.16%, which is very promising. Providing this metric transparently shows that our model isn't just theoretically sound, it performs well in practice. Before any model training begins, we do careful pre-processing. Healthcare data can be messy or inconsistent, so we clean and normalize the input. We also focus on selecting only the most relevant features like TAL, CT, and CA, which are clinically meaningful. This helps the model avoid overfitting and makes the result more reliable and easier to interpret for medical professionals. And finally, clear communication is key. We need to go beyond the technical explanation and speak in terms that non-experts, especially decision makers, can understand. For instance, we highlight how early prediction through the model can lead to earlier interventions, better outcomes, and cost saving. When stakeholders can both see the clinical and economic value, they are more likely to adopt the technology. Now, let's talk about ethics. Even if a model is highly accurate and well designed, it won't succeed or be safe if it is not used ethically. Here are the main concerns we address. So, the first, patient privacy is a top priority. All data used must be anonymized and compliant with strict regulation like HIPAA in the US and GDPR in Europe. This means removing personally identifiable information and ensuring secure handling at every stage. Maintaining privacy isn't just about following laws, it is about respecting the dignity and trust of patients. Second, healthcare professionals need to understand how and why a model makes a certain prediction. If they cannot explain a recommendation to a patient, they won't use the tool. That's why interpretability is not optional, it is essential. We prioritize model where the logic is transparent, so result can be communicated clearly and confidently. Third, bias in training data can lead to unequal treatment across groups, such as based on race, gender, or age. To avoid this, we perform fairness audits and use techniques that make the model more aware of potential biases. The goal is to ensure equitable prediction regardless of who the patient is. Four, AI should be seen as a support system, not a replacement for human expertise. It can aid decision making, but clinicians must still apply their judgment. We make sure this message is clear to prevent blind reliance on the system, which could lead to unsafe outcomes. Lastly, healthcare isn't static. Disease evolve, treatment protocol change, and patient population shift. So the model must be regularly monitored and updated to handle concept drift and stay accurate. Continuous evaluation ensure the model remain useful and safe over time. In conclusion, building trust and ensuring ethical use are the two pillars of successful of AI adoption in healthcare. When we prioritize transparency, accuracy, and fairness, we can create tools that truly support clinician and improve patient outcomes. That's all from us. Thank you.